we are now moving into the heart of this course, that is the transistors. I hope you all had a chance to watch the video lecture from last time. It's a little bit lengthy because it involves derivations, mathematical derivations, physical principles. The physics is very easily lost in this process. So let me summarize what we have discussed so far. Okay, so let me do the summary here. So we have basically derived, which we will not redo it here, the drain current of a FET, and it is expressed in the expression here. It's mu n Cox times aspect ratio, W over L, times OV over drive, VDS minus 1/2 VDS square. Okay, a lot of symbols, a lot of subscripts. It is unavoidable, and we need to be very carefully distinguishing that. We often have a symbol to represent mu n Cox, Kn prime. These are largely dependent on the technology node that you selected. You selected a fab, you selected a technology that you're going to implement your circuit. This is by and large fixed. W over L is at the discretion of circuit designer, so you have the freedom to change usually W, usually you keep L as a standard gate length. We often also lumped W over L together with a symbol Kn. Symbols in these CMOS transistors, they are more or less universal. So sometimes people got used to it. Circuit designers or engineers in the field, they simply refer to the symbols without explaining what it is. So that's, it's a very prevalent. So we're going to look at this expression, what it means, the physical meaning of that, and what's actually happening in the transistor here. So if you plot this curve, if you plot the IV curve, which is ID versus VDS, and using VG as a parameter, okay? So remember, we are talking about NMOS, okay? So this is NMOS, and this is gate, okay? This is source, this is drain. VDS is basically here, VDS. VGS is the voltage between the control gate and the source, okay? So this is the transistor of interest that we are discussing here. And the transistor usually have a threshold voltage. So we assume the threshold voltage to be VT. And we usually write VT subscript N to explicitly indicating this is a threshold voltage for NMOS. Okay, so this is an NMOS. Later on, we will talk about PMOS and eventually complementary MOS that includes both N and P. The threshold voltages are usually different for N and P. So it is important to keep track of the individual threshold voltages. So coming back to this equation that we spent a lot of time deriving, you will recognize that as if we use a VDS as an independent variable, this is a parabolic curve, okay? So you'll see is roughly something like this. And there's a maximum happening, okay? You can find the maximum relatively easily. So you take a derivative. Let me do partial derivative since we have many variables here. Partial derivative of ID versus VDS. Okay, you set that equal to 0 and ignore the constant. You'll find the VOV minus VDS equals 0. So basically, we call these maximum current ID set. So there's yet another terminology. This we call ID set. We'll explain what set is later, okay? And this happens when basically VDS equal V overdrive. And just to remind you, V overdrive is equal to VGS minus VTN. Okay, so the amount of gate voltage you apply to the gate beyond threshold voltage. Okay, so far so good. This is kind of the high level circuit parameter picture. So now we kind of move in closely to what happened in the device. So let me draw a cross section here of this MOS, okay? And we have source, drain, and gate, okay? And gate is shaded here. So this is gate, this is N plus doped, this is source, this is N plus doped, this is drain, okay? And the substrate is P doped, okay? P doped substrate. And in the normal operation, we will bias the gate with a positive voltage to a point that there is, to a point there is a lot of positive charges here. And there will be electrons induced in the channel, okay? And so this is called inversion layer because it's electron inside a p-type material, which usually holes are abundant, but electrons are scarce. We have applied sufficient voltage to overcome the potential and induce the electron to come out from the source terminal. And if we plot, so this is a MOS picture. Now, as we apply VDS to the transistor, so imagine we are applying basically VDS to the transistor. So this is done by, for example, ground the substrate, and we apply basically VDS here, okay. The channel potential is actually not uniform. The channel potential, as in the recorded the video, the channel actually has a variable potential. Depends on exactly where you are or the electrons are in the channel. So if we were to plot the potential, so let me plot a spatial distribution of potential V, okay? In the spatial coordinate X, okay? So let me draw a dotted line here and the dotted line here, okay? And if we ground source, okay, so potential is 0, so it is 0 here. And the entire source, because it's heavily doped, we can think of it almost like a metal. So the entire source is same potential. And entire drain is also same potential. Initially it's 0 and there's no current. When we just raise the VDS slightly, okay, so it is equal potential here, okay. Let's call this VDS1, okay. So X put it down here. So this is VDS1. So we just gradually increase that. Important potential as a reference is this gate potential, is overdrive potential. Okay, so this is an important reference here. So let me draw a dotted line here. Okay, this dotted line is V overdrive. So this is a VGS over VTN. And this number, of course, changes every time you change gate voltage. For now, let's fix the gate voltage. So this gate voltage is independent of position. So it's just a constant. So it's a straight line across X here. And our lengthy mathematical derivation last time basically says, well, the channel potential kind of vary in between source and drain. We did not assume it to be linearly varying, okay? But at low voltage, it's pretty close to linear. But you don't need to assume the specific relationship because we simply integrate over the entire area. For the sake of illustration here, I'll simply draw a straight line, okay? But you can explain it even though the actual potential deviates from straight line. And so this corresponds to the IV curve somewhere here. Okay, let me draw a blue dot here at the low bias. Let me switch to a color. Let's say if we increase the voltage more, okay, we reach somewhere here, okay, and this is a VDS2. So somewhere here, we raise our voltage more, ID increase. Okay, there are more electrons in the channel. They conduct more current, okay? And we can keep going until we reach this point. Well, we exactly reaches here, okay? So at this point, VDS is equal to V overdrive. So we reach at this maximum point where current reaches maximum. We can gain a little bit better understanding if we plot also at the same time our electron density. So if I plot N of X, these are electron density per unit area. So these are electron density, but this is per centimeter square, okay? We don't, the thickness, we already consider the thickness in there. So basically, N of X, we need a little bit more space. N of X is basically Cox, the gate capacitance, times the voltage difference. So think of this as a capacitor. So on the one side is VG, VGS. At the other side is channel potential Vx. And it is the excess voltage above VTN that will generate electrons. Okay, so this is the threshold voltage is simply the nonlinear characteristics of the MOS capacitor. The voltage is the linear part, okay? We can simplify this to COX and times VGS minus VTN. This is simply V over drive, V over, minus V of X, okay? So if we look on this potential plot here, this is basically, if we take I need to put a broken line here. source has lots of electrons, drain has lots of electrons. This come from doping. This doesn't come from bias. It just come from doping. And now let's take again these three cases. For the blue line, the difference is very large. So there's a lot of electron near the source, slightly less, but still a lot of electron in the drain. So we have basically a curve like this, right? And let's move to the green curve. When we raise the VDS, well, the difference between overdrive voltage and VDS diminishes towards the drain. On the source side, it's the same. Okay, so we'll have a curve, something like this. Okay, that's our channel electron density distribution. Now let's go to this orange line here. Orange line at the drain is a singular point where the voltage difference is now exactly 0. So if we use these capacitance, it means it goes to 0 here. Okay, and that's the point we reach the maximum current. Now, if we further increase the current, further increase the VDS, we will expect to, well, reach this point. Well, let's see whether that's physical or not. So we further raise VDS 4, which is now higher than overdrive voltage, okay? If we apply our kind of extension of what we've done, if we have a dotted line here, right? And look what happened if we track the this electron charge density. So we will be crossing a 0 somewhere here. So let me draw a dotted line here, and then you will extend over to the other side. Now this is not so physically intuitively possible. If we look at this overshoot here, a negative electron concentration, does that mean holes? Okay, the energy is favoring for holes to appear here now. But let's look at the structure again. This is a electron source, electron drain, and around the channel, there is a depletion region. Let me take this color here. So there is a depletion region here. Okay, so inside, this is a depletion region of a PN junction. If you remember, of a PN, there's no holes in the depletion region. So there's no supply of holes here. What happened is instead of having hole appearing here, the electron will indeed goes to 0 at this point, but it wouldn't go to the opposite side. It will stay 0 here. Okay. What does this mean? This means, well, the potential distribution is now slightly different. The electron distribution is more like it will follow this orange curve here. Okay, roughly, not exactly, but after it crosses, after the electron become, actually, let me draw it this way. So it should be something like this, okay? And then the slope change, it becomes higher here, right? So these high field region, so now we create a high field region near the drain, but this area has no electron. So this area has no electron. So we have essentially in this area, we so-called pinched off the channel. If you think of channel as a water pipe, this is the time we actually fully pinch it off. There's no electrons there anymore. Are there still current flowing? Yes, there are still current flowing. So even though the electrons are, we don't have electrons here, but we have still a lot of electrons in this early part. This electron will be accelerated towards the drain at high velocity because of the higher field. So just like even in vacuum tube, you have electron in space, you put a voltage, the electron will accelerate to the bias electrodes. So this is the same thing here. So what we have basically show you in this physical picture is, well, this is not a physical picture. The curve, the current will not decrease, but rather this electron distribution will stay largely the same and modify slightly by these pinch off region, okay? So to first order, this curve should continue as a straight line and not following down as the original formula we derived. All the formulas are mathematical models, so it shouldn't, we don't need to be alarmed if the mathematical model fail to describe the physical behavior. Why does it fail? Well, remember in our derivation, we assume there are electrons everywhere in the channel. And naturally, when there are areas when electrons are pinched off, channels are pinched off, our earlier model is not strictly valid. It's only valid up to the point there are electrons in the channel, okay? How do we know what is the current when the channel pinches off? Well, when the channel pinches off, you can go through the same derivation and you just integrate over the area, but it's more easier to look at it. Physically, it's the same, roughly the same channel electron distribution, and the current simply go straight here. So the IV curve should really looks like ID, VDS. It's a parabolic curve. Right at the point it reaches maximum, it levels off, okay? And the transistor, we have different name for each regime of operation. In this regime, okay, we call this triad regime, okay? If you wonder what is a triad, you know of a diode. What is a triad? This terminology stems from the vacuum tube technology. Remember, the transistor was invented to replace a vacuum tube. So at the transition, it's very easy for people simply using the vacuum tube technology. And this regime is called saturation. Okay, we will talk more extensively about these two regimes. At this point, any questions about the explanation for the pinch off condition? So the pinch off condition happens basically when VDS equals the overdrive voltage, okay? Anytime you apply higher voltage, pinch off happens and the current become almost constant. Okay, yes, question?
So in that region where electron density is basically zero, in reality it's not actually zero because it's no velocity, so there's
Yes, so the question is in this pinch off region of the channel, that the electron cannot be possibly zero because there are electrons flying by from the non-zero part of the channel to drain where electron got drained. Indeed, that is the case. There's no steady state electron concentration there, but electrons are flying by at very high velocity very quickly through that pinch-off region. If you compare with the electron velocity, it's much slower in the part that's not pinched off. There are so many electrons, so the nature of the current conduction there is just like metals. So a lot of electron moving at the slower speed. Then in that pinch-off region, is very few electron moving at a much higher speed. Current is the same. Any other question? So this is the important conceptual part. And once you understand the concept, you can will gradually extract it to higher level. When we talk about circuit problems, will be basically just based on this curve here. So this curve, as we mentioned, there are two parts. Okay, the trial region can be modeled by ID is equal to mu n Cox W over L V overdrive VDS minus 1/2 VDS square. Okay, and after it reaches maximum, it entered, because this is called saturation region. So this current is called ID set. Okay, set stand for saturation, and we just substitute VOV in VDS by VOV. So you'll find this is equal to 1/2 mu n Cox W over L times V overdrive square. So very simple expression. And note that it is independent of VDS because it's a straight line. So it's independent of VDS. Once the channel pinches off, further increase the drain voltage to the first order does not change. Okay, hopefully we are back. So this is the same picture. So this is a voltage or channel potential, okay, source, drain, and it goes roughly linearly, okay? And this is V overdrive here, V overdrive here, and VGS. So VGS is VT threshold voltage higher than V overdrive. And at the bottom, it's plotting kind of the electron distribution. This is equivalent to my plot of n of x here. These plots, which is abundant in all textbooks, have led many students to think this is how electron distributed, that electron extend over a thicker region near the source. This is not the case. The electrons are exactly at the interface, very, very thin sheet of electrons that are there. This thickness here simply represent there are more electrons near the source, okay? And this is the pinch-off point. There are 0 electrons at the pinch-off. So this is when just about to to enter this saturation regime. Okay, and once you enter the saturation regimes, this is the expression. So this is what we commonly write as ID set to distinguish it from the earlier triad regime. Okay, so we cover this. Any questions? No? Okay. So again, same thing. We have described it again. This is kind of a summary. There is a trial regime. Trial regime happens when your drain bias is less than this critical voltage, V overdrive. You need to keep in mind this V overdrive is a function of VGS. When we change VGS, V overdrive change, okay? And when you are over that, we are in the saturation regimes, okay? In the saturation regime, it's a simpler expression, okay? So far, so good? Okay, so remember the VGS is a variable, okay? So what we have just discussed is one VGS curve. So imagine we just talk about this first curve, VGS curve, okay? A transistor being a three-terminal devices, there are really two independent voltages, VGS and VDS. We have only two-dimensional plot, so it's very difficult to visualize all the variables. So what is commonly used is we do a two-dimensional plot, ID versus VDS, but using VGS as a parameter. So there are multiple curves. Each curve corresponds to different VGS. So for example, VGS, we increase the VGS to the second curve. Now there's a same expression. So there's a second curve, there's a parabolic curve, and again, it's saturated, okay? When you increase VGS more, here's another parabolic curve, okay? And ID set. Note that the current become higher and higher, okay? And if you check the expression, so in the saturation regime, ID set is equal to 1/2 mu n Cox W over L, and then V overdrive square. So as we increase VGS, ignore the threshold voltage part, we are effectively increasing the overdrive voltage, okay? Imagine if we double it, if we have a constant overdrive voltage, then if this is 1, this should be 4 if we have equal spacing of overdrive voltage. After squaring, you go 1 to 4, and if this is still equal spacing, this should be 9, okay? And if this is equal spacing, this will be 16. So this will be non-uniform curve. It's getting farther and farther away from each other, okay? So this is due to this square dependence of overdrive voltage. And if you look at the horizontal axis, this maximum point, as we mentioned, this happen when VDS equal V overdrive. Now, if we increase V overdrive, and they will happen at different voltages, okay? And again, the graph looks like they are almost equal increment, okay? If we go from, say, overdrive of 1 volt, overdrive of 2 volts, overdrive of 3 volts, and overdrive of 4 volts. And the maximum current goes by the square dependence. So the boundary between them, this boundary is a parabolic curve. So if you look at this boundary, okay, this boundary between triad and saturation itself is also a parabolic curve. And this parabolic curve is basically this curve, okay? It's basically this curve. this is the boundary. This is the boundary of, let me just use a different color to highlight. So this is the boundary. The green line is the boundary. And this boundary curve is represented by this equation here. So it is a simple equation that explains all the behavior of the transistors. Okay. Questions so far? And please review this part after you go home. When you are studying, read the textbook. It's a very important concept. Once you understand that, you feel you're comfortable applying that to circuits when we discuss circuits. Okay, so the same curve, remember we have really three important parameters in a transistor. We have ID, we have VDS, we have VGS, okay. And VGS, again, is V overdrive plus VTN, okay. We also can plot ID versus VGS, since all apply the input voltage to a common amplifier. So plot current versus VGS, and you'll follow these equation here. Well, it's the same quadratic curve, okay? This quadratic curve, if you take a square root of both sides, then if you plot instead of ID, you plot the square root of ID, and you vary the gate voltage, it becomes a straight line. And experimentally, you can plot this from your measured current, take a square root, and then extrapolate, okay, extrapolate where the zero intercept is the threshold voltage. So this is how you can find the threshold voltage experimentally. If you don't know the threshold voltage, so this is how you will find it. And I would encourage you to try that in the lab. It may not, I think it may be required, even if it is not required, just to verify whether what we learned is correct or not. Okay. Any questions? There is a caveat about all these beautiful theory, and unfortunately, I have to tell you that this beautiful theory that explains everything is good for the transistor you use in the lab. It's good for transistors up until probably year 2000. This is so-called the long channel devices. The channel is still relatively long. When the channel becomes shorter and shorter, our simple concept, the potentials are really not predominantly in one direction. It's really the three-dimensional picture. And this device, so-called square law device, you'll often hear, we call this a square law device. Square law because of the dependence on the square of the overdrive voltage. They don't describe accurately the small transistor behavior. Is there an alternative theory? Yes, there are a lot of alternative theories, but as transistors become so small, the alternative theory ran out of steam again. And so there keeps coming up with newer models. Eventually, the community have decided basically just develop a model that has a lot of parameters. It no longer have these beautiful closed forms. It's just a gigantic equation with, I don't know, close to 100 parameters to describe the current. That's only when it is accurate enough to model the circuit behavior. So that's the sophistication that it has gone into the modern transistors and modern circuits. Nevertheless, these two lectures are not wasted in vain. The physical concept, physical intuitions is still very well developed under this sort of simpler model. Just give you a caution that in case you're talking to engineers, circuit designers, that you know there are revisions of the model. Okay, all right. There is a complementary type of MOS transistors. You flip N and P totally. So you start with N-type substrate. You dope your source heavily into P-type, so it's P+. You dope your drain heavily, so it's P+. The gate voltage, now you will apply negative bias. Okay, there's a different threshold voltage, but you would apply negative voltage relative to the threshold voltage, and this will induce positive charges, holes coming out from the source, and the whole physics is the same. So we don't need to derive it again. It's basically the same physics. You just have to change basically the polarity of the current direction, the polarity of the voltage. We will go through the current equation for P MOSFET later on. So don't worry about it for now. So the construction looks physically very simple. One thing that we have talked about before is, for the same equation, so ID is still the same. It's mu P Cox times W over L and times, I'll put the absolute value sign here because the sign flip. Overdrive voltage, VDS, okay, minus 1/2 VDS square, okay. I put the reason I put absolute value sign is the polarity of the voltage switch for all these for PMOS. One thing to note is, it's now proportional to the mobility of holes. And remember, for silicon, okay, mu n is about 3 times of mu p. This is just a material property. Different material, they have different ratio. But for the abundant silicon, majority of the ICs, 99.9% of the ICs are made of silicon. And this is the material we are dealing with. What do? It's usually inconvenient to have different current for PMOS and NMOS. So you compensate for the current by the width of the transistor. So so we often, okay, use 3 times width or W for PMOS. Okay, so then the current will be roughly the same. If you look at the physical layout, your PMOS are usually bigger than your NMOS. Okay, and CMOS, so concept appear in the early 70s. Initially, it was just another new idea, but eventually has become the dominant ideas. And because as we learned in the at the beginning of the lecture, or what you learned in 16A and B, we usually have PMOS in series with NMOS. Okay, so your circuit looks like a lot of chains of these type of circuits. Okay, so there's an NMOS, PMOS usually on top, and there's an NMOS usually at the bottom. You can use your kind of digital picture you learn from 16AB. When the voltage, if you kind of think of as an inverter gate, you tie the voltage together. You turn on NMOS. So when this voltage is high, you turn on NMOS. At that time, you shut off PMOS. Or alternatively, you lower the voltage. In this case, PMOS is on, but NMOS is off. So they are never on at the same time. One of them is always off in digital circuit, which means there's no DC current that flows from your power supply voltage, VDD, to the ground. And that's a huge saving of power. This is to be compared with the NMOS logic that precedes the CMOS logic. NMOS logic, we will use a resistor to bias the NMOS, okay? You can still do inverter using this structure, okay? When the voltage is on, okay, and the NMOS turns on, okay. At this time, there is current. The current is flowing through the low resistor, okay. So there's a current power consumption, ID times R. And every little transistor have a resistor. They add up when you have billions of them. It's actually not possible to go to such a large integration. The power consumption will be too large. So only with CMOS, cutting down the DC current, the current only flows when you are basically charging your low capacitor, as we mentioned at the beginning of the lecture. The current only go to charge the capacitor, or in the alternative case, you drain the charge on the capacitor. It consumes power during that very brief period of time. Once the charge are in place or drained, there's no power consumption. So this turns out to be the most important logic families. And all the transistors you look at, usually it contains both NMOS and PMOS. The very first question you have is, well, they require different substrate. NMOS require P-type substrate. PMOS will require N-type substrate. Well, if we are integrating them on the same substrate, we have only one type of substrate. So luckily, we can change locally where the transistor sits in. So we put the PMOS inside so-called an N-well, okay? So locally, it's just like they have a P-type, they have an N-type substrate. And then you have same doping type for the source and drain, okay? Modern transistor actually also put the NMOS on a P-well, okay? So this gives us more flexibility in controlling the environment each NMOS sits in. If you want to do an absolutely simplest process, then you eliminate this P-well. But for more precise circuits, usually it's called a twin well. You have P-well where NMOS sits, and then you have an N-well, sorry, P-well, NMOS sits, N-well, PMOS sits, okay. All right, so that's the CMOS concept. We will, in most of the circuits we are going to introduce, we have NMOS and PMOS, but we don't operate it in the digital regime. We operate it in the analog regime. Any questions so far? So we will be transcending the physical picture into the models. So we'll be now focusing on the larger signal models. That is when the voltage swing from rail to rail, from ground to power supply voltage, and then to small signal model when we bias the transistor and the signal just vary adjacent to that DC bias value. Okay, all right. So let's go to the next module. the large signal models, okay? And soon, your next lab, you'll be dealing with a bias circuit. So it's important to talk about bias circuit. So the beginning, the first slide is basically review of what we have earlier. It's identical slides. So trial region, saturation regions, okay? And so this is the large signal model. What is large signal model? Basically, this is the large signal model. These two equations. These two equations are large signal models, okay? Large signal models are not necessarily linear, okay? Like a diode, a large signal model is that exponential expression. That's the large signal model, okay? Small signal model, we linearize it around the particular bias point, okay? So we talk about the large signal model of ID versus VGS, the exactly same slide we just gone through, okay? So, this is a beginning of a discussion of an amplifier. So here we're just simply looking qualitatively at this amplifier circuit. The amplifier consists of NMOS. NMOS is the active element. So this is the only circuit element that's producing gain. Everything else is passive. So we have just a resistor here. Resistor, capacitor, inductor are called passive elements. So this is a simple circuit with one transistor, one passive element, okay? And we can kind of picture how it works qualitatively. So we will bias a transistor at some DC bias. So capital V, capital G, capital S. This usually means it's a DC bias, okay? Small signal, all VGS, all V and G and S, all small case, these are AC small signal, okay? Remember our convention is a VGS, capital G, capital S, is equal to VGS plus VGS. Okay, so total signal is equal to DC plus AC. Okay, you need to have good eyes to spot the subscript. You may blame people who develop all the initial formulation, but really we are running out of symbols. There's really not that many choices, okay? So this is a commonly used convention. We'll stick to that. First, we understand the basic concept, the bias curve. So this is called the transfer curve. So this blue curve here, this is called transfer curve of this transistor circuit. We can qualitatively think like this. When VGS is very small, so horizontal axis is VGS, the vertical axis is VDS, so VDS is here. Think of this as output voltage, and the VGS as an input voltage. So output versus input, the transfer curve of this amplifier. When VGS is very small, so think of we are just varying this battery here. And when it is very small, NMOS is turned off, okay? And the VDS, okay, VDS is basically equal to VDD minus ID times RD, okay? And ID is very small when the transistor is cut off. When the transistor cut off, ID is equal to 0. So you got this flat part of the curve. Okay, let me switch. So you got this flat part of the curve. Actually, let me switch to red color. And as ID gradually turn on, so finally above the threshold voltage, okay, VGS is higher than threshold voltage, ID starts to be non-zero, and as ID increase, this will start to decrease, okay? And eventually, when VGS is fully turned on, then the voltage drop across the NMOS become very small. Most of the voltage drop goes to the resistor. So it's kind of like an inverter type of characteristics. Eventually, the output voltage is low. For digital circuits, we operate at the beginning, okay? We operate at the beginning and the end. So when input is low, we have high output. When input is high, we have low output. In the analog amplifier, we try to pick up very weak signals, okay? So we will bias the transistor in between the high and low state, ideally kind of roughly in the middle. So roughly 1/2, this will be roughly 1/2 of VDD, okay? So there is a sufficient swing in both directions. The output can swing up towards VDD, it can swing down towards ground, okay? So this is the case here. And then we superimpose our input signal. So now we put our input signal. So this is our bias point. We usually designated Q, quiescent point, as a bias point. So this is a DC bias. It's a capital V, capital G, capital S. Then we superimpose, if we draw another curve as a function of time going downward for the input signal, the AC signal will be kind of dancing around the DC signal. And you can trace point by point. This point will go to this point, right? So this point, you go to this point, and it goes to this point here. The second point, when it crosses the DC point, it goes to here. So this point will go over here. If the horizontal axis is again time, and you will see that the output signal as input is traversing through the downward, the output curve is traversing through, basically you're sliding back and forth in this part of the transit curve, transfer curve. So you're basically just going up and down. As your input voltage reduces, you slide up. As your